Yeah. So hi everyone. This is the Ruby Developer Book Club, and today we are winding up with Ruby and a microscope. So I'll be covering chapter 12, and this is about the various kinds of garbage collection, both in Maths Ruby interpreter, then the one that is used in JRuby, and then the other one that's used in Rubinius. So that will be the scope of the discussion. So I'll start with a bit of a background about garbage collection as a term. So here, what the purpose of a garbage collector is that it's going to first and foremost create memory for new objects. That's if you create new objects, for example, in an IRB session. In addition to creating memory for new objects, it's going to clean up old objects that you no longer need, such that the memory that you end up with is used for newer objects. So I think those are the two main uses of a garbage collector. And here the introduction lets us know that Ruby is not the only language that has a garbage collector implemented in it. The first language being Lisp. I haven't tried this, so I don't know if you guys have tried it.
Lisp?
Lisp.
Yeah,
Yeah.
I've played around with Lisp a little bit, yeah.
And it's
Mhm.
interesting because Ruby
Okay.
was the original Ruby math interpreter was not object oriented. It was originally a Lisp, and then he changed his mind.
Oh, that's interesting. I didn't know that. That's super interesting. I wonder what
Well,
happened. I
object
wonder if
Oh,
oriented
he
was
got
like
more and
new
more
and
into
all the
small
rage,
talk.
so he wanted to
Yeah.
experiment with it. But it was originally a Lisp.
Interesting.
yes, I had also read somewhere that Ruby borrows ideas from small talk, though I don't know if that's true or
Yes.
not.
Yeah.
Yes, it's very, very much like small talk, yeah, in a lot of ways.
Okay. So that aside, we'll now start on the actual roadmap. I'll be starting with okay. Garbage collectors solve three problems, like I've mentioned: allocate memory for use by new objects, and then identify objects which are the program not using anymore, so that we free up the memory they've been occupying, and reclaim that memory for use by new objects. So those are the three main uses of a garbage collector, or the problems that are solved by a garbage collector, any kind of garbage collector. So first and foremost, we'll look at the mark and sweep algorithm, which is I think the implementation we see in the garbage collector in Maths Ruby interpreter. And here we'll be looking at how it operates theoretically, and then after that, we'll be proceeding to the actual implementation details. For example, the marking, how the marking happens, and then of course the sweeping, because it's called mark and sweep. Yeah. So we have something called the free list, and as you can see on figure 12.1, so as Ruby creates objects for you, each of these squares that you see in the free list is supposed to be occupied, is a memory block that is occupied by a new object that you create. So let's say you've created a new object. Your very first object will occupy the very first square, and the second object you create will occupy the second square, and the third object that you create will occupy the third square in this free list. So there's a bit of color coding that's going on here, whereby it's good to mention that the gray boxes signify that that memory block has been taken and is not available anymore. And then the white, or the unshaded box, signifies that memory block in the free list is available for use by any new Ruby object. So as you keep on creating more objects, of course, these squares will keep on being used up to the point that at a certain level you're going to run out of squares. So what are you going to do then? These are some of the things that we'll look at later on when we are looking at the details of the marking and then the sweeping. So one other thing I would want to point out, which is relevant for the coming subsections, is that in this free list, all Ruby objects are represented by a C structure called the R value. And then one key thing about this kind of algorithm, as you can see that the squares themselves are of the same size, is that this algorithm has no way of determining the kind of object that you're dealing with. So it has no way of knowing whether this will be a string or whether this will be an array or a hash. And therefore, it also has no way of determining the size of that object. And this is something that we'll see that differs from another kind of garbage collection algorithm that we'll look at later on. So there's this note here, and it says that when MRI starts to execute a Ruby script, it allocates memory for use in the free list that we've seen before. And this says that the initial length of the free list is set to about 10,000 R value structures. Remember that each of these new objects is represented by an R value structure, regardless of what type of object it is. So you have 10,000 R value structures, which means that you can create 10,000 new objects to occupy the 10,000 R value squares. Let me call them squares. So as more objects are needed, MRI, the Maths Ruby interpreter, allocates more memory, placing more empty R values onto the free list. And then another thing to note is that rather than create a single long linked list with 10,000 elements, the memory that you end up allocating is divided into subsections called heaps, of which each heap is 16K in size. I'm not sure what the K means. Is it kilobytes?
Yeah. Yeah.
Yeah, 16 kilobytes in size. And then these heaps will be filled in such a way that the first heap is filled first, and when it's filled, now we move on to the second heap, and then the third heap, and so on and so forth in that order. So I'll move on to the marking. Remember, the algorithm is called a marking and sweeping algorithm. So what we are trying to do here by marking is that we are trying to identify which objects are still needed by the program and which objects are not needed anymore. So the objects that are needed by the program, for example, the saved objects, will be referred to as live objects. And then the objects that are no longer needed by the program will be referred to as garbage objects. And one thing to note is that regardless of whether the object is live or garbage, all these objects are occupying memory. So our aim here is that we are trying to identify which are the garbage objects, and then we'll free up the memory that is occupied by the garbage objects such that it can be used by the new objects that are soon to be created. So when you look at figure 12.4, we see a bunch of squares, and then we see arrows that are diverging from each of the squares. So the very first square that you see on the left is what is referred to as the root object. And this is a global variable that you create, or an internal object that Ruby knows your application must be using. Though I'm not sure if you guys had researched about an example of this internal object.
I have not done any research about that. I mean, it makes sense that you have to have at least one root so that the algorithm has a place to
Yeah,
start. Um,
yeah.
but yeah, I haven't done any
So
actual research.
my understanding is that there can be more than one root. So
Yeah.
a root just represents like an object in the either the global namespace or just a top level object. Like, you have a whole bunch of concept. When your application starts up, it makes a bunch of objects, and
Oh, constant.
those would be the top level
Yeah.
objects.
Yeah, I
And then
think
you
in here,
create other ones that are like either referenced by those or contained by those, and those are not top level.
yeah, somewhere in
Mm.
here it suggests that if you make something a global variable, that becomes another root as well.
Oh, yeah,
Yeah, it
yeah.
says right there. Yeah. So if you
So,
create like ten global
mm,
variables, it sounds like you've added 10 new root
root
level
root
objects.
object. Oh, okay. So, like I've said, the very first box, the gray box that you see in figure 12.4 is the root object. And as you see, these arrows actually, um, the arrows, I could say, the arrows represent references from the root object onto the other object. And as you can see, we start off with two arrows that are coming from the root object and then to two other objects, of which now these objects themselves have arrows that originate to them to reference to other objects that have potentially been created. So one thing to note here is that this entire figure 12.4, is what's called an object graph. Yeah. And given that at the introduction I talked about us having live objects and garbage objects, at some point you're going to have an object graph that looks like what you see in figure 12.5. And what you see here is that the gray squares signify live objects, while the unshaded squares, which are white, are used to represent the garbage objects that are on that current heap. So what we are going to do here, at least throughout the process, is that we are going to reclaim the memory that is occupied by each of these garbage objects, and we'll make it available for the new incoming objects that are soon to be created. So this following section goes into detail about how the interpreter marks live objects, and this is based on a technique called bitmap marking, whereby the live object is marked as a series of bits in a data structure known as a free bitmap. Though I'm not sure if this thing of 0101 is what is called a bitmap, a free
Yeah,
bitmap.
yeah, it is.
Okay. And then another question that I had about this diagram is the fact that the few arrows that come, okay, not arrows, but the few lines that come from the free bitmap onto the free list, or yeah, the free list, we see that from zero, you have a line coming from zero and pointing to one unshaded square. And then when it comes to one, you have a line originating from it and pointing to a shaded square. So my
Mhm.
question is, are the zeros only paired with the unshaded squares and the ones only paired with the shaded squares, or this was
Yeah,
just a
no, that's
coincidence?
exactly it. No, that's what
Yeah,
those ones mean, that those objects are live. That's why they're shaded.
Oh, okay.
yeah.
So another.
So the
Mhm.
the reason that they're using zeros and one there is that it's instead of creating like an array with integers or booleans, an array with booleans would take up more space in memory than it would be to represent it as zeros and ones, because zeros and ones uh, is just an integer by itself. And so that integer by itself, the places in that integer uh, represent, like if you have a zero in this one place, it maps to uh, the memory location being either used or not used, claimable or not reclaimable memory.
Okay. So another thing to note here is that this free bitmap that we end up seeing is saved in a separate memory structure, which is not near the where is not near where the objects themselves are saved initially. And apparently, the reason as to why this saving happens in a different memory structure is for optimization reasons. Though I'm not very familiar with the details about this copy on write optimization technique. But all it says here is that by saving the MAC bit separately, MRI maximizes the amount of memory that will contain the same values across processors. I don't know if you guys have anything
So
Well, we
like,
to.
oh, go ahead, Miles.
I was gonna say it might have to do with forking. For one thing, it is common in Unix, so you might fork a process and it sounds like so when you fork a process, the memory gets copied to a new location, and now you have two processes that start off with the same exact values, and then they diverge from there. Sounds to me like Unix is able to lazily copy over some. I didn't even know that it could do this, but it sounds like it has some ability to lazily copy stuff over from one process to the other when it changes, if that makes sense. So this might have to do with forking, but I'm not exactly sure.
Oh, Nelson, you had something to say.
Yeah, it was more or less that. It's basically just saying like instead of doubling the amount of memory that's going to be used, we're going to share some of this memory as long as it stays the same.
No. Okay. So moving on, now we'll proceed to tackle the sweeping part, as the name says, mark and sweep. So here, what we are trying to do, like I've said, we are trying to sweep the objects that are referred to as garbage objects, such that we create new memory for incoming objects. And then, as you can see here in the diagram, we have these arrows that are pointing downwards, and they are originating from each of the garbage objects or objects that are not needed anymore. And then we are adding we are adding the memory that was occupied by these garbage objects back onto the free list that we started with initially. And of course, one thing you can see is that the length of the free list, I assume, will depend on the number of garbage objects whose memory you've managed to reclaim. So, hypothetically, if you had only two gray boxes here and the rest of all those boxes were unshaded, of course, this free list would be longer than it is currently. So here it states that the process of moving unused objects back onto the free list is referred to as sweeping the object. And then normally the process runs very quickly because the interpreter doesn't actually copy the object. It simply adjusts the pointer in each R value to create the free linked list. And the issue of the pointer here, this is something we looked at when we were covering those the structures of each of those objects. So this R value structure has a pointer, and that pointer will be referencing what kind of object it is. So that is the pointer that this statement is referring to.
Uh,
So yes,
Newton, sorry, I'm gonna go off on a tangent here, but do you know what a linked list is?
a linked list.
Yeah.
No,
Okay.
but
So
I've
the
heard.
free list is implemented as a linked list, and it's one of the things that you learn when you study data structures and algorithms. But those arrows there, uh, they they're pointers from one node to the next node. So at some point, it's important to learn about like data structures. So you'll learn what a linked list is, and this is one example of when you would use a linked list.
Oh, so the arrows show that it's actually linked. The arrows from one box to the other show that each of these boxes are linked together.
Yeah,
It's a list of things that are linked together.
yeah.
Yeah,
Uh,
that diagram looks incomplete too because that at some point you would point to the previously existing free list, and he doesn't show that here. But that crossed my mind when you were talking about the length of it. But there's more to there usually be more to the free list than just so here they're sweeping 4 items into the free list.
Yeah.
But this isn't the entire free list here. So I kind of feel like there's a missing pointer on the right to link it to the rest of the free list. Anyway, don't worry about that if that doesn't make sense. Just something I noticed.
Oh, okay. So one thing about this mark and sweep algorithm is the fact that for the garbage collector to run, the program has to be stopped, and this is one of the reasons as to why you have this optimization technique, which is referred to as lazy sweeping. And here the lazy sweep algorithm is aimed at reducing the amount of time for which the program is going to be stopped such that the garbage collector runs. So I imagine lazy sweeping to be a kind of sweeping that I can describe as incomplete. Like it doesn't sweep everything at once, but only what is needed at the time when the garbage collector runs.
Yeah.
Yeah. So that is how I imagine it to be, and it's just an optimization technique that's meant to address that time issue associated with the mark and sweep algorithm in MRI.
There's something I can mention that I've mentioned before, but maybe it'll make more sense now or whatever. But way back in Ruby 1.8.7, a like kind of a hack or whatever we used to do is when the Rails request would start, we would disable the garbage collector. And then when the request was done, we would re-enable the garbage collector. And this just made the request way, way, way faster because the garbage collector in 1.8.7 was pretty bad. But this basically prevented it from stopping in the middle of the request response. So as long as you had enough memory to handle the request, it made it a lot faster.
Yeah.
And this kind of highlights why that was at the time.
Yeah, GitHub did the same thing. And in this era, computers were of a certain speed, and actually, we'll see that the more memory you use, the slower it is. So some of these garbage collecting sweeps, at least the long ones, could take half a second. And if your request, your web request takes 200 milliseconds, and then an extra 500 milliseconds for the garbage collection, all of a sudden you're waiting a good portion of a second for that request, and it really slows down your 99th percentile speed times. So
Yeah.
yeah.
Okay.
Oh, Newton, did you do any research outside of the book, like on the newer approaches?
Yeah, I tried to, but it became confusing pretty fast.
Okay.
So, yeah.
I can talk a little bit about the newer approaches too. Once
Please
once
do.
you're finished with this section.
Oh, okay. So, like I've mentioned, the lazy sweeping technique is meant to address the amount of time and potentially reduce the time that your program waits for while the garbage collector is doing its work. But then one thing to note is that while lazy sweeping can actually help you reduce the time, it doesn't reduce the amount of work or the total amount of garbage collection that ends up happening. It's just that this lazy sweeping, what it does is that the collecting is done in turns as opposed to it being done at once. And then another thing to note is that this lazy sweeping happens in the context of the current heap. So when Ruby tries to lazy sweep the current heap and it can't find any garbage objects on that heap, it moves on to the next heap. And then if the next heap is similar to the current heap in that it doesn't have garbage objects as well, it then moves on to the next heap. So it kind of moves in that fashion. I didn't really go through this R value structure, but maybe you guys have something to talk about it. I don't know, but I hadn't
Well,
gone through it.
he points out, I think the most interesting part, he points out at the bottom there, he says, notice at one that our value uses a union. So what that means is that when you, so see how you have that R basic pointer there or struct there, that R basic struct.
Yeah.
When the object is live, that R basic struct like has meaningful things in it. Um, but when it gets marked for being put into the free list, instead that gets clobbered with that flags and the pointer to the next R value. So the thing to point out there is that yeah, there is this pointer in the R value structure to point to the next node in the free list in that linked list, but it doesn't take up any additional space. So that's kind of a I don't know if that makes sense. It would help if you already knew C, but I know that you're not familiar with or not that familiar with C Newton. But basically, that union basically means these things share the same memory as each other.
Yeah. But sometimes you're wasting memory, right? Because some of the smaller bits have to get shared with some of the bigger
Right.
values. And so sometimes you are using more space than you actually need to. And that's
Yeah.
actually one of the approaches that was addressed in the newer garbage collectors. I don't know if I
Yeah.
should talk about it now or I guess maybe I shouldn't talk about it now. So in the newer garbage collector, instead of a single R value sized R value struct, now you have it divided into different sizes. And so instead of using a single R value union for all the objects, you have them split up into objects that share similar amounts of space. And what that allows is you waste less amount of space, but also all the things that are of the same size get put together in the same region of memory. And a lot of times when you're accessing those regions of memory, it's faster to put similar things together because they're more likely going to be accessed together. And that's faster than spreading them out all over the place.
Yeah. They're more likely to be in the CPU cache, which comes up later in the chapter
Oh,
too. Yeah.
yeah, I think that's part of the one of the algorithms that he ends up mentioning in the coming section. Yeah. So um I think I'm going to try to speed run through this because we have 7 minutes now so that I finish this. So disadvantages of the mark and sweep algorithm. First and foremost, the one I mentioned before is that the program has to stop and wait for the garbage collector to do whatever it's doing. Even with the lazy sweeping technique, this can still affect the performance of your application. And then another thing is that the time that's required to perform the mark and sweep garbage collection is proportional to the total size of the heap. So the greater the heap, the greater the time that is being taken to perform the garbage collection. And then another thing that I talked about initially was the size. As you saw that those boxes were of the same size. So you can see that the final issue with mark and sweep is that all of the free list elements, i.e. the unused objects available for the program to use, must be the same size. And this is because the interpreter doesn't know ahead of time when you create a new object whether this object will be a string or an array or a number. Yeah, because initially we talked about this interpreter using an R value structure as opposed to any of these structures that you see here. For example, R string, R array, and R regexp. So we know that this interpreter defaults to the R value structure as opposed to the specific structures, which maybe could have pointed to the kind of object we are dealing with. So this is an experiment, and it's meant to show what happens when you try to perform a mark and sweep garbage collection by running this loop. And one thing to note here, I'll proceed with the results themselves. First and foremost is that the total field doesn't change. And I think, let me see, the total field displays the value that MRI returns for object space count objects. This value is the total number of objects currently active inside Ruby. And of course, this I assume includes the free, no, the live object, sorry, and then the garbage objects, I suppose. And of course, all these objects may be objects that you have created yourself, which is by running the program, or the objects that are created by Ruby itself when it's, for example, executing your program. And then we have this second column, which is the free field, and this is the length of the free list. And as we can see, as we keep on creating more objects, because the last field is related to object creation. So with every new object that you create, you can see that the available number of free lists, the available memory boxes in the free list keeps on reducing. And you can see that from the very first line, you have 171, and then you go to 139, and then you go to 132. And he mentions that the difference between, okay, the average distance between each of these is roughly 7, because Ruby creates 6 other objects in addition to the one object that you've created. So 6 plus 1 is 7. And of course, if you look at the very last field, you can see that the increment is by 1. They keep on increasing by 1. Though I'm not sure about what the other 6 objects that are created by Ruby. I'm not sure what they are.
Yeah, I don't know either.
So yeah, that's basically the gist of that. And now we move on to another experiment that goes on, that describes how the interpreter performs a lazy sweep. And here, I think we'll proceed with this in the next meeting because we have 3 minutes. Yeah. So I'll see you
Okay.
guys in the next meeting.
Okay. See you over there.